Welcome to Maths with EJD. In this video, we're talking about Laplace transform of periodic functions. Um, when we look at different types of functions, especially when I consider types of functions in basic calculus, one of the functions we saw is the idea of periodic functions. That's functions that take the same value after a regular interval. Okay, and trig functions like sine and cosine are very good examples of periodic functions. So let's go for the idea of Laplace as it relates with this kind of functions. The Laplace transform of periodic functions simplifies solving differential equations involving periodic inputs. Okay, so a function f of t with period t satisfies f of t plus t equals f of t. That means that the function comes back to the same thing after every period t. Okay, and that happens for all t greater than or equal to 0. So that's the idea. So this is the basic idea of periodicity. So a function at t is exactly the same after a particular period, big T, like that. So let's consider Laplace transform for periodic functions. Okay, so if f of t is periodic with period t, its Laplace transform is given by the Laplace of f of t, which is the same thing as 1 over 1 minus e raised to power minus s big T, integral from 0 to t of e raised to power minus s t f of t dt. So this is the usual thing we should have, right? But because of the very nature of periodic functions, right, we have this expression outside here, in addition to the regular thing we know. So but normally this is actually from 0 to infinity, I think. But here, because it's now 0 to t because of the periodicity, we have this balancing that out actually. So this formula, this formula converts the integral over all time into a simpler integral over a single period. That's why we have the factor outside. Over a single period, 0 to t, exploiting periodicity. Exploiting periodicity. Okay, so let's have this and then this. So let's take example one. Example one, something about square wave function. Square wave function. Okay, consider the periodic function f of t equals 1 when 0 is less than or equal to t, which is less than or equal to big T over 2. That's the period over 2, and the function is 0 when t over 2 is less than or equal to t is less than t. So that's a square function. So, and it is repeating with period t. So what do we do if we want to find the Laplace? So the first step 1 is to compute the integral, over one period, just like we had up there. So that means the integral from 0 to t is of e raised by minus st f of t dt is integral from 0 to t over 2, based on what we have, right? 0 to t over 2, it's 1 there. So 0 to t over 2, e raised by st multiplied by 1, dt plus integral from t over 2 to t e raised by minus st 0 dt. So automatically this will be gone, so that we now have this now to be equal to integral from 0 to t over 2 e raised by st dt. And what that simply tells us, e raised by minus st actually, I hope that was the right thing I did initially. That expression, or the very first expression here, it should be minus, it's minus e raised by minus st. It is e raised by minus st. So from this now, we just know this is, when you integrate that, we have e raised by minus st divided by minus s from 0 to t over 2. That's big T over 2. So this is equal to minus 1 over s can come out into e raised by minus st, e raised by minus st from 0 to t over 2. So this is minus 1 over s into, when we integrate now, and when we put the values, we have e raised by minus s big T over 2 minus e raised by minus 0, okay? Because once t is 0, that's s into 0 now. So that will be equals to minus 1 over s into e raised by minus st over 2 minus 1, okay? Plus e raised by minus 0 is 1 over e raised by 0, which is simply 1. So if we tidy that up now, we simply are going to have, you know, 1 minus multiplies by 1. So we have minus e raised by minus st over 2 all over s. So that is the integral. That is the integral from 0 to t over 2. Or, I mean, overall, right? We can look at the big picture. That's integral from 0 to t e raised by minus st f of t dt. So that's all we have for that right there. Okay, so with this now, we can, I mean, that one, the second integral has vanished already. So applying the formula, that formula we saw the other time, applying the formula, what do we have? That's L of f of t. So we have, applying the formula now, that is step 2. Step 2. Applying the formula, we now have L of f of t equals 1 over e raised by minus st integral from 0 to t e raised by minus st f of t dt. But now this has been found to be this expression up there. So we just have the Laplace of f of t to be equal to 1 over 1 minus e raised by minus st. Okay, I didn't get this quite right. Yeah. 1 over 1 minus e raised power minus st equals, so here now we have 1 over 1 minus e raised power st. Okay, let me write everything properly. Some perfectionistic thing going on right here. Okay. All right. So here, this is 1 over 1 minus e raised power minus s big T integral from 0 to t e raised power minus st f of t dt. And this we have obtained up there. So we can bring it down. And then we have that the Laplace of f of t is equal to 1 over 1 minus e raised power minus s big T multiplied by 1 minus e raised power minus s big T divided by 2 all over s. And that is what we have. That's the result. We may just want to tidy all of that up. So the Laplace of f of t is now the same as 1 minus e raised power minus st over 2 all over s into 1 minus e raised power minus s big T. And that is the result for a square wave function. Okay, so this comes and then we move on to say this now. So example 2. So for example 2, we have what we call the sawtooth wave function. Sawtooth wave function. So in this case, we say let f of t be equal to t for 0 less than or equal to t less than t, and periodic with period as usual big T. So then we go step 1. Step 1, we compute the integral over one period, So that means that integral from 0 to t e raised power minus s of t f of t dt is the same thing as integral from 0 to t of e raised power minus st. F of t now is t dt, because that is what we have from here. So with this now we need to do integration by parts because this is t, right? So here, this can be our u and this is our, this together. Okay, let me do another. So this is u, right? So this put together with this is our u dv. I mean, is our v du rather. V du. So in that case, this is exactly equal to the same thing as uv minus integral of v du. And what that simply means is that since u is t, right? That's simply t. Then, okay, I think this is, we have u, right? And then this has to be v du. Yeah, v du. No, not v du. So everything together is dv. So the whole, okay, I think the writing is causing trouble for me. Let me rearrange better for easy referencing. So, what I'm simply saying here is that this is the same thing as integral from 0 to big T, t e raised power minus st dt. Yes, this is what I need. So now this is u and this is dv exactly. So that the integral of that whole thing is now uv minus integral of v du. Okay, uv minus integral of v du. If you don't understand what I'm doing here, you can revisit my work um on integration by parts. So this is, so everything of course is from 0 to t, right? So everything is from 0 to t. So if we go by this now, we have Uh, so we now have integral from 0 to t e raised power minus st f of t dt is equal to u. Our u is t. So if u is equal to t, that implies that du dt is equal to 1. That means that du is equal to dt. So then we also have v, right? So if dv is equal to e raised power minus st dt, right? So that simply implies that when we integrate, so v alone is going to be e raised power minus st all over all over minus s. That's minus 1 over s e raised power minus st. That is what that's going to be. So that's by the way. So we need that idea to do what we want to do next. So to get v, right, we integrate this, and that is minus 1 over s e raised power minus st. So u, we differentiate to get du. So we have uv, u is t, v is minus 1 over s e raised power minus st. So this is uv from 0 to t, first of all, and as integral of v du. So v now is minus 1 over s e raised power minus st. Okay, and du is simply dt. Okay, du is simply dt. So we can tidy this up, and we have minus 1 over s can be out. Then we have t e raised to minus st from 0 to t minus this minus minus is plus. 1 over s can come out. So we have integral e raised to minus st dt, and we can continue. So this is minus 1 over s. Of course, this is also from 0 to t. The integral is from 0 to t. So we have minus s into t e raised to minus st from 0 to t plus 1 over s. When we integrate, this is from 0 to t for sure. When we integrate that, now we have again e raised to minus st all over minus s from 0 to t. So we can also bring that out. So we have minus 1 over s into t e raised to minus st from 0 to t. Then, because of the other minus that is coming into the play now, okay, we have plus and minus, that's minus, and we have 1 over s squared into e raised to minus st, 1 e raised to minus st from 0 to big T. So this is equal to minus 1 over s into, put big T for t. So we have t e minus s big T, put 0, and that is just done. Then minus 1 over s squared into, put t again, we have e raised to minus st. Okay, put 0. Yeah, put 0. Okay, yeah, 0 works here. So if you put 0, that will just be minus 1. Okay, because that'll be minus e raised to minus s times 0. Okay, so but here, because t is also 0, that's why it will just cancel out. So again, we have the integral from 0 to t of e raised power minus st f of t dt, and that is simply the same thing as uh t. We can say that is minus t e raised power minus st all over s minus, here plus can go in, so we have okay, so we can have this to be minus e raised power minus s big T minus 1 all over s squared. So we can have it that way, and then try to tidy up all of that. So we have t e s t all over s. Yeah, so we can, the minus can go inside, right? So we have minus te minus s big T, then plus 1 minus e raised to minus st, because the minus goes inside, plus comes forward, all over s squared, so that we can still have 1 minus e raised to minus s big T all over s squared. Okay, this is over s, sorry, minus t e s big T all over s. So that is the integral, but then we have to apply the formula. So step 2, we apply the formula. Step 2, we apply the formula. So if we apply the formula again, the formula tells us that the Laplace of f of t for a periodic function is 1 over 1 minus e raised to power minus s big T, then integral from 0 to t e raised to power minus st f of t dt. And since we have got this part now, so we have the Laplace of f of t to be equal to 1 over 1 minus e raised to power minus s big T multiplied by, or I mean, I can just put that down so I don't have to worry again. So this is 1 minus e raised to power minus s big T all over s squared minus te minus s big T all over s. And that's the result we get finally for that. So this is what we get. So this is what we get. Now, that brings us to the end of that. So just know this is like the most important thing to know in this situation now. That for a periodic function, that's what it looks like. Then the main work now is then to just look for the integral part, depending on the nature of the of what you have, right? Um, here we just have f of t to be t. But if it is a square function, you have to evaluate all the step parts of it to get the actual results. Okay, so let's move this here now, and then say we have this. So practice. Can you try some things out? Practice the following. Um, so what do we do? Compute 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 the Laplace of f of t for the following. So number one, you have f of t equals 2 when 0 is less than t is less than 3, and 0 when 3 is less than or equal to t is less than 6. That's the first one. Number two, f of t is equal to sine t when 0 is less than or equal to t is less than pi. Number three, you have a triangular wave f of t equals t for 0 less than t for 0 less than t less than 2, and 4 minus t for 2 less than or equal to t less than 4. Okay, then let's take a fourth one. Let's take a fourth one where f of t is equal to 3, 0 less than or equal to t less than 2, and 5, 2 less than or equal to t less than 4. Then number five, you have f of t, a square wave, which is 1, 0 less than or equal to t less than 1, and minus 1, 1 less than or equal to t less than 2. Let's get something more serious. 6, f of t is e raised to power minus t, 0 less than or equal to t less than 1, and then 0, 1 less than or equal to t less than 2. Then number seven, uh, Laplace transform of a pulse train, say f of t is 1 for 0 less than or equal to t less than or equal to big T over 4, and then it's 0 for big T over 4 less than or equal to t less than or equal to t, like that. Okay, so that's what we have in that situation. Let me see your answers in the comment section, either on Facebook or on YouTube. Let me also know in the comment section how helpful these videos have been for you. And feel free to let me know also if there's a topic you'd like me to teach, a problem you'd like me to solve. Then if you have subscribed already, I thank you so much. If you have not subscribed, please go ahead and subscribe, because there's a lot for you to learn on this channel. And everybody don't forget to hit the notification bell so you can always get alerted each time a new video is released. And be sure to share and like and share uh, this channel or this video or any other part of this channel you think will be useful to people you know, so more people can have access to these great things going on here. Till I come your way again, keep doing maths right. Bye.